In this video, we're going to start looking at mechanisms. So most of the reactions that we're going to be doing after this chapter, we're going to be drawing mechanisms for them. And a mechanism shows all electron movement. So it's going to show every single step of the reaction, all the bonds that we're breaking, all the bonds that we're forming. It's going to show intermediates, and then sometimes we're going to show transition states also. So it shows every step of the reaction. It shows all electron movement. So those reactions that I had you doing earlier in the semester where we were identifying nucleophiles and electrophiles and we were showing our nucleophile, right, our curved arrows going to an electrophile, that's that electron movement. Essentially what we were doing there is we were showing mechanisms. So we're going to show all electron movement. We should put the word all in there. Right? All of the bonds that we're breaking, all of the bonds that we're forming. It's going to show all intermediates. Do you remember from 152 what an intermediate was? You would have defined it in your kinetics chapter, so chapter 12. Yeah, good. So intermediate was something that we're forming in one step and then consuming in a subsequent step. Comparing that, or contrasting that, we should say, to a catalyst, right? A catalyst is something that we put in and then get out. So in that kinetics chapter where you were given the steps of a reaction and you had to write the overall and you would cross out the things that were the same on the product and the reactant side, right? Our intermediate was going to be a product first and then a reactant, right? It's something we're making and then using up. A catalyst was first a reactant and then a product, right? We put it in and then get it out. So it shows all intermediates. These are formed in one step and consumed in a subsequent step. And then sometimes we're going to show transition states. If we don't have any intermediates, then I do ask that we show a transition state. We always have transition states, we just don't always need to show them. So sometimes shows transition states. And a transition state is the state where our bonds are partially formed and partially broken. So if you were going, just kind of as an example, if you were going from A and then you were reacting it with BC and you were forming AC plus B, right? That's what we're forming. So to get from point A to point B, I'm having to break the bond between B and C, and I have to form the bond between A and C. And let's say this was a one-step reaction, so I don't have an intermediate. So what I would do is I would end up breaking that bond between B and C at the same time that I'm forming that bond between C and A. So when we draw dotted lines like that, that's my transition state. So partial, right? Partially formed, partially broken. The bond between A and C is partially formed. The bond between between C and B is partially broken. Common notation is to put brackets around it, and then we put that double dagger symbol. And we are going to look at energy diagrams. When we do that, I will kind of show you how it fits in there, but they are going to be our highest energy state. But we're going to go from my reactants essentially to that transition state and then to my products. Again, we're always forming transition states. I'm just not always asking that we show them. Sometimes we will. If there's an intermediate, though, we show all of them. So every step of the reaction gets shown, all electron movement, every bond that we're breaking, every bond that we're forming, all of our intermediates. Intermediate is something that we're going to form in one step and then consume in a subsequent step. And then sometimes we're going to show our transition states. We'll just do a quick example of a mechanism. Like I said, we've seen a few of these when we've been identifying nucleophiles and electrophiles. All those arrows we've been drawing are showing that electron movement. So I'm going to do an addition reaction. So I'm going to have my hydrogen and my chlorine. My alkene is going to be my nucleophile. I know that this hydrogen is partial positive because of its polar bond to chlorine, so that hydrogen is going to be my electrophile. So those are going to grab onto hydrogen, and then hydrogen can only have 2 electrons. So if we're going to form a bond to hydrogen, we have to break a bond from hydrogen, and those electrons are going to go onto chlorine. What I have now is I have this intermediate. So I ended up putting the hydrogen on one of those 2 carbons. I actually put it on the first carbon, right? I had 1 hydrogen here and 1 hydrogen here. I now have 2 here, but I still have 1 here, so it does have that positive charge. I have chlorine floating around, or chloride, I should say, right? It has that negative charge. So it's going to be attracted to that carbocation, right? That non-octet carbon. It's a pretty bad arrow, but it's being attached to that, attracted to that, and then I have my product. So this one in the middle here, my non-octet carbon, my carbocation is the name of that, is my intermediate. HCl would be my reagent. So I showed breaking my pi bond, right? Those electrons are grabbing onto hydrogen. I'm also forming the bond between that carbon and that hydrogen, right? That same arrow. I'm breaking the pi bond at the same time I'm forming a sigma bond between carbon and hydrogen. I'm breaking the bond between hydrogen and chlorine, and then I'm forming a bond between chlorine and my non-octet carbon. So this would be an example of a mechanism. I would have, again, transition states, right, if I wanted to draw them. And something like this, because I have an intermediate, I wouldn't ask you to. I'm just going to draw them because I want to reiterate what it is and reinforce the fact that I always have them. So if I was to draw my transition state for my first step, so the one that exists where that arrow would be, I'm breaking that pi bond, I'm forming a bond between carbon and hydrogen, and I'm breaking a bond between hydrogen and chlorine. So all of those lines would be dotted. So my transition state for that one, I'm going to have a dotted line where that pi bond is because I'm breaking it. I'm going to have a dotted line between that hydrogen and my carbon because I'm forming it, and then a dotted line between that hydrogen and that chlorine because I'm breaking it. So if I was to draw the transition state that goes here, this would be it, right? We always have them, right? I have to break the bond, so we're always going to have a transition state. I just don't always show them. And then if I wanted my second transition state, the one that would go here, I am just forming a bond, so I would have a dotted line between that carbon and chlorine. And then again, it's a transition state, so our usual notation. So between my reactant and my intermediate, we would have this, and then between my intermediate and my product, we would have this. Again, you generally don't have to show them if there's an intermediate. As we go through specific reactions, I'll be very clear as to whether or not I want you to draw the transition state or not. So a couple ways we can break bonds. So bond breaking or cleavage. So our first one is homolytic, and this is going to be symmetrical breaking. And even though we're going to introduce this in this semester, we're not going to really see a lot of examples of this type of bond breaking. In 236 you will, though. So homolytic, and this is symmetrical. So lytic, if you lyse something, you're breaking it. And then homo, they're both going to the same side. So essentially we're dividing the electrons equally. And we have not seen these yet this semester. All the ones that we've been doing have been both of the electrons going in one direction versus being equal. So an example, if I had A bonded to B, and remember that line is 2 electrons, right? A bond is 2 electrons. So what I'm going to do is I'm going to give 1 electron to A, and I'm going to give 1 electron to B. How we've seen it is both electrons going in one direction. So this is a new one for us. The arrows that we draw are going to be called fishhook arrows. So if we go back up and look at the arrows we did up here, notice how I have 2 barbs on it. It's a normal looking arrow. A fishhook arrow is only going to have 1 barb. So we're moving 1 electron. We're only going to put the little part on one side of it. So I'm going to take one of these electrons. I'm going to give it to A, and then I'm going to put 1 hook on it. Right? Don't do this. That's incorrect, right? We want our fishhook arrows. 1 electron, 1 barb. And then our other electron is going on to B, so also 1 barb. So a fishhook arrow. I did them both up. You could do them both down if you wanted. You could do 1 up and 1 down. That might even look better, but long as 1 electron goes onto A, 1 electron goes onto B, and our fishhook arrows, right, the arrows with 1 barb is how we're denoting that we're moving 1 electron. So what I have is 2 radicals. I have A that has 1 electron, and then I have B that has another electron. So we've produced radicals. A radical is an atom with an odd number of electrons. It has an unpaired electron. Has a lone electron. Not a lone pair, but a lone electron. The second way are the ones that we've been doing. So these are heterolytic. This is going to be unsymmetrical. So one of the 2 atoms gets both of the electrons. So if I had A bonded to B again, and I'm going to give the electrons to B, this time I'm going to put 2 barbs on my arrow, right? Because I'm moving 2 electrons. And then A in this case lost those electrons, so it's going to have a positive charge. And then B gained those electrons. It has an extra lone pair, and it has a negative charge. Generally, we do require energy to break a bond. So both of these, I would have to put energy into it. And we're going to produce intermediates. So generally, energy is required to break a bond. And then it usually produces intermediates. Some common intermediates. Again, remember, an intermediate is something we're producing in one step and then consuming in a subsequent step. So they are quite reactive, right? We're not done at this point. So we're producing something that is pretty reactive because we're going to use it up. So they generally are high in energy. They tend to be unstable. They tend to have a short lifespan. So generally high in energy, right? They're reactive. If something's high in energy, it's reactive. Right? If it's low in energy, it's not reactive, it's stable. They're not as high in energy as a transition state. Transition states we can't even isolate. You can isolate an intermediate, but transition states are going to be our highest energy state. These guys are also high, but not as high in energy as a transition state. So generally high in energy, making them unstable, right? They have a short lifespan, if you think about them as living. basically you make them and then you use them up. They don't stick around for very long because they are high in energy and reactive. So common ones, first one is that radical. We're not going to really see a lot of those this semester. We're really only going to see them in this chapter. And then in 236, you will do some mechanisms, learn some reactions where you have radical intermediates. So carbon radicals. Again, remember radicals mean I have a lone electron. So carbon, and then I'm putting 3 R groups on it. In this case, an R group can be a carbon or a hydrogen. So essentially I have a carbon that's bonded to 3 other things. When I'm putting an R group there, it doesn't really matter what it is. It's just 3 other things. And then a lone electron. So R in this case could be a carbon-based group. So I could have a methyl group, an ethyl group, a cyclobutyl group. It doesn't really matter. Or a hydrogen. So it is tetrahedral because I do have 4 electron groups, right? That lone electron needs to be in an orbital, right? Electrons are in orbitals. And actually, I'm going to turn that hydrogen back into an R so it's not confusing as to why I'm switching it. I don't mean to be. So they could be carbon groups, they could be hydrogens. So it is sp3 hybridized. It is uncharged. If you do the formal charge calculation, it doesn't have a charge, right? 4 is my number of valence electrons for carbon. And then 1, 2, 3, 4, right? Lines and dots. So 4 minus 4 is 0. So it is uncharged. However, it's non-octet, right? That carbon has 7 electrons around it, not 8. That single electron is what makes it reactive. Electrons want to be paired. So if it's a single electron, it tends to be reactive. It's actually going to go steal an electron from something next to it, and then that thing ends up with a single electron, and then that goes and steals an electron from something else, and then it becomes a radical. So radical reactions tend to be chain reactions. So single electrons make it reactive, not reactant. Sorry guys. Reactive. So for all of these, I want you to know like what they are. So know what a carbon radical is. Know its hybridization, and then know like what makes it unstable, right? These guys are high in energy. Why is it why is it an intermediate? Well, it's not octet, right? It has that single electron that makes it reactive, right? It wants to be paired up. Our second one are carbocations. These are the intermediates that we're going to see mostly this semester. And just as it sounds, it's a cation on a carbon, so it's a carbon with a positive charge. To have that positive charge, it is going to be non-octet. So it's actually going to be sp2 hybridized. My carbon is only going to have 3 electron groups around it. And I'm going to draw those 3 electron groups in not the plane of the screen, but coming in and out at you. So that's coming out, and then this is going back. So trigonal planar, but I'm drawing the plane coming in and out. And then remember, if it's sp2 hybridized, I do have that p orbital on there. And it's empty, right? Making this a Lewis acid. Right? I have an empty p orbital. It's electron poor because it's non-octet. It's electrophilic. Do you want to put my formal positive charge on there? It looks kind of naked without it. So sp2 hybridized. It does have a formal positive charge. It is non-octet. It is electrophilic, right? It's electron poor. We don't think of radicals as being electrophiles or nucleophiles because when they react, I'm going to show us ways we form bonds, and we're going to have a similar version to our homogenic bond breaking where each of the two atoms is contributing an electron. So you don't have source and receptor, they're both sources, and then they kind of meet out in the middle. So electrophile and nucleophile aren't going to apply to radicals. So carbocations, right, are non-octet carbon with a positive charge. It has an empty orbital that we can put electrons into, right? It's my electrophile. And then my last one is going to be a carbon with a negative charge, so a carbanion. So carbon with a negative charge, which means it has a lone pair of electrons on it. So when I draw this one is going to be sp3 again. That lone pair has to be in an orbital, right? Electrons are in orbitals. So sp3 hybridized. I do have a formal negative charge on that carbon. Oops. So sp3, it has a formal negative charge. It is octet, right? That is an octet carbon, but I do have a negative charge on a not very electronegative atom, and that's what makes this unstable. Carbons just don't handle that negative charge well. So we could say the negative is on an atom that is not very electronegative. It just can't handle that charge very well. It is nucleophilic, right? It has that lone pair, it's my electron source. Bond formation next, right? We broke some bonds. So we had bond cleavage, either breaking it symmetrically or unsymmetrically. If we break it symmetrically, we ended up with a radical intermediate. If we broke it unsymmetrically, we could end up with carbocations or carbanions. And now we're going to form bonds. So bond formation. And we're going to have the two ways to do that also. So this time, instead of lytic, it's going to be genic because we're forming it. So one, homogenic. So this is going to be symmetrical. So I'm actually going to start out with radicals, and then each of them is going to contribute an electron. Again, because I'm going to be moving one electron, I am going to use those fishhook arrows. So A is going to contribute an electron, B is going to meet them out in the middle, and we're going to end up with forming those bonds. I drew one up and one down. You could do them both up, you can do them both down. It only matters that you use the fishhook arrows and you meet somewhere in the middle. So I formed that bond, right? A contributed one electron, B contributed one electron. I don't think of it as a nucleophile and electrophile because they're equally electron rich and equally electron poor, right? They're both non-octet. They both have a free electron, a free radical. And then heterogenic. This is our unsymmetrical one. So this is where I do have an electrophile and a nucleophile. So in this case, I'm going to have A with a positive charge, so it's electron poor. I have B with a lone pair of electrons. It's my electron rich site. I'm going to go from my electron rich to my electron poor, right? From the source to the receptor, from the nucleophile to the electrophile. And I'm going to have two barbs on my arrow because I am moving two electrons. And I now have a bond between A and B. All right, this was my nucleophile. This was my electrophile.